Greetings to all. Title of the paper is Axial Behavior of Concrete Filled Double Skin Steel Tubular Column with Concrete Imperfection. Key objectives are to experimentally study total 14 CFDST columns of outer circular and square steel tube and inner square steel tube with circumferential and spherical cap-cap ratios under axial compression loading, and second is to investigate the behavior of CFDST columns in terms of ultimate strength, ductility, failure modes, confinement, strain distribution profile along the length, and to propose a new strength prediction model for CFDST columns with concrete imperfection. Mechanical properties of structural steel were evaluated with tension test performed on coupon extracted from circular and square HSTs as presented here, and self-compacting concrete with characteristic compressive strength of 27.5 MPa with following mixed design was used as infill for CFDST columns. The prepared CFDST column test specimens with pinned end conditions were instrumented as shown and were tested under axial compression loading. Experimental results of CS CFDST and SS CFDST columns show severe reduction in axial capacity with CCI as compared to SCI. Axial deformation curves depicts multiple kinks and higher ductility in SS CFDST columns owing to the local buckling as compared to the CS CFDST columns, which mainly fails with a global buckling mode. Confinement mechanism have been studied with experimentally measured strain ratio. The deviation in strain ratio suggests initiation of confinement of concrete from outer steel tube. Square-shaped CFDST columns show early deviation owing to plate bending as compared to the circular CFDST columns. Test results are compared with analytical results evaluated following modified EC4 equation proposed by Paglatov et al. Apart, this comparison study is further extended with strength index considering both the types of concrete imperfection cap ratios. The ultimate strength prediction model is proposed for CS CFDST and SS CFDST column, incorporating the effect of different types of concrete imperfections. Finally, the following set of equations are suggested to accurately quantify the confined, unconfined, and partially confined area of concrete, which can be further ascertained with FE analysis. These are the key conclusions of this study. Circumferential gap imperfections for CFDST columns exhibit a higher reduction in axial capacity as compared to spherical or rectangular gap imperfections. The ductility of CFDST columns was found to decrease with an increase in concrete imperfections. However, square-shaped CFDST columns yield relatively higher ductility as compared to circular-shaped CFDST columns owing to multiple local buckling near the support. Confinement mechanism demonstrate that confinement effect for CFDST columns diminishes with an increase in concrete imperfection gap ratios. Proposed strength reduction factors for CS CFDST and SS CFDST columns based on experimental studies provide a good estimation of axial strength for CFDST columns with concrete imperfections. Thank you.